Okay, so last time we were talking about topological spaces, okay, and that was sort of a precursor to talking about manifolds. So today we'll continue our discussion on topological spaces, and next time we'll start on manifolds. So as you've seen, topological spaces are essentially about sort of points or a set, and sort of talking about neighborhoods of points, okay, or more formally, right, what we defined was a topological space as a set X, okay, which is the set of points of, let's say, our space-time. That's what we're going to think about eventually, and a collection T of subsets of X, okay, and these subsets are called open sets, okay, they're given the name open sets, and this collection of subsets satisfies three properties. One is that the null set and the full X belong to T. Second is if you take any subcollection of these open sets, okay, and you take their union, then the union of those also belongs to T, okay. And also if you take any intersection of a finite subcollection, not necessarily, definitely not an infinite subcollection, but the only requirement is that a finite subcollection. If you require that a finite subcollection of them, their intersection also belongs to T, okay, then you say that T gives a topology to X, okay. And we've seen a few examples of different types of topology, okay. So we had this discrete topology, and we had the trivial topology, and then the one that we're going to be interested in is the usual topology on R, which can be extended to a usual topology on Rn, okay. So this is the set of so in this case X. So for example, if X was the real line, the T was the set of all open intervals on the real line and the union of all such open sets. Okay, sorry, open intervals rather. Sorry, I should be clear about the terminology. Okay, so intervals refer to things that are defined on the real line. Okay, open intervals on the real line. Open sets refer to topology. Okay. So it's just, in mathematics, you just want to be precise about what these definitions are. So it's good to separate out what we mean by open set. It's a very specific term. It refers to one of those sets in T. Okay. Okay. So today we're going to just continue some of our definitions. So we just looked at a couple of properties of these topological spaces. Okay. So last time we looked at things like induced topology. So if you take a subset of X and X has a topology, then that subset A also inherits a topology from X. Then we talked about continuity and continuous maps between two topological spaces. And for example, if we take the real line with the usual topology, we saw that the topological notion of continuity is similar to the notion of continuous functions. Okay, so continuous maps are really just continuous functions between real numbers. Okay, in the usual sense of continuity that you learn in calculus using epsilons and deltas. Okay, and the last thing we did was we defined what are called neighborhoods. Okay, and what is a Hausdorff space. So roughly the idea was that you can take a neighborhood. Neighborhood doesn't have to be an open set, okay, or a union of open sets. It can also be closed, partially closed, and so on. And only condition is it should contain the point X that you're talking about, and it should also contain at least one of your open sets UI, which belongs to your topology T. And we defined a Hausdorff space to be one where if you have a topological space X and I have 2 points X1 and X2, then it should be possible to find neighborhoods of these such that the neighborhoods are disconnected from each other. That is, the intersection of the neighborhoods is an empty set. Okay. Okay, and in practice, all the spaces that we'll talk about will be Hausdorff. Okay, and so Rn with the usual topology is Hausdorff. Okay, so let's continue this discussion of topological spaces. Yeah, I see a question, Sushil.
Sir, I didn't get that point that in a real line is not a Hausdorff space.
Real line is a Hausdorff space.
Is a Hausdorff. Means,
it
but
is also.
how the neighborhood of any 2 points is disconnected in that case?
In the sense that I can always, if I take any 2 points on the real line, right, I can always find a neighborhood of this point and this point, right, that basically I can consider, for example, an open set around this and an open set around this, such that these two are disconnected. It's possible to find such neighborhoods.
Uh,
Right?
but once you mentioned that even for an open set, like from 1 to 2, there is a closed set. 1 to 2 is a neighborhood for open set 1 to 2.
Yeah, that's right. So 1, 2 is, so if I, okay. So these are two different things. Okay. It's not that any neighborhood satisfies this criteria. It's what I'm saying is it's possible to find a neighborhood that satisfies this criteria. So for example, if this is the point 0.5 and 0.75, it's true that the neighborhood of 1, 2 contains both is the neighborhood of both 0.5 and the neighborhood of both 0.75. Okay. So in this case, you have, if I define the neighborhood of 0.5 to be 1, 2, and the neighborhood of 0.75 to be 1, 2, then it's true that these are overlapping. Okay.
Yes.
But I could always find other neighborhoods of 0.5 which are smaller, right? And a neighborhood of 0.75 which is also smaller, such that these two neighborhoods don't overlap.
So the smallest neighborhood.
Yeah, you can think about it as smaller neighborhood, but basically the claim is that there exist neighborhoods that don't intersect.
Okay, got it.
Okay, yeah, so neighborhoods are more general, right? In the sense you can define neighborhoods as big or as small as you want them to be. Okay. Okay, again, these classes, next few classes are going to be pretty mathematical, but I would also say that for physicists, knowing these ideas of topological spaces and manifolds is useful even beyond general relativity. There are many places where even though your classes may not have been taught using the context of manifolds, you can really think about these things in the context of manifolds, and a lot of things become more obvious. For example, things like classical mechanics, thermodynamics, a lot of this can be thought about manifolds, and maybe I'll talk a little bit about those connections at some later point. Okay, so it's just good to go over this formally. Okay, and even though GR textbooks typically don't start with discussing topology, okay, it's good to start from the starting point of topological spaces, then go to manifolds, and then metric spaces that we look at. Yeah, so Soumyadeep?
Yes, sir. Can you go back to the slide where you were just defining continuous?
Continuous.
Yes, sir. Yes,
Yeah,
sir. In
here?
this example, yes, sir.
Which one? This
In the
one?
later
This one?
parameter. Yes,
Yeah.
sir. If we take the interval which is like in positive y and negative y, then how will it map back to x?
Positive y negative. Okay, so let me be clear about one thing. Okay, so in the last class, so I mentioned this just after the class, after the recording stopped. So when I talked about a map from x to y, okay, the first thing is that map didn't have to be onto, which means it doesn't cover the whole y. Okay, so for example, y is equal to x square, right? The map doesn't cover, let's say, the whole y. Okay, so this one, right? So as you're saying, the negative y is not covered by this map. Okay, and secondly, the map need not be one-to-one. Okay, which means that so it means that for a given value of x, that maybe two values of y or multiple values of y, which means the map itself is not invertible, but you can still define. So what do I mean by this f inverse? Okay, f inverse is just a symbol. You shouldn't think of it as the inverse function. What I mean by this is what is called the inverse image. Okay, so what that means is, so supposing I take an open interval in y. Okay, so in this case, in the example that I done in class, I said let's take this open interval in y, and let's look at the inverse image. So that is, we're looking at the set of points in x that give rise to these points in y. Okay, so so we look at this. Okay, and the set of points here, okay, is these points, and I find their inverse image in x, it is these points, and similarly I find the inverse image in x in these points. So let me call this set S1 and S2, and the union of S1 and S2 is the inverse image, okay, which I'll denote as UI. It's an open set in X, okay, open set in the sense of topology, and this UI prime is an open set in Y, okay, and that was our definition of continuous functions. If an open set in Y has an inverse image, which is an open set in X, then we say that the map is continuous, okay, in the sense of topological continuity, which we're seeing is in agreement with the notion of functional continuity, okay. Now the question is, so what if I had chosen my open interval to be like this? Okay, now the point is that these points over here in Y don't have an inverse in X, so that I can think of the inverse image of these as sort of the null set in X, okay, and these points have an inverse image, okay, and that as long as I choose an open set in Y, okay, that these points, okay, let's say up till here, have the inverse image which lies, let's say, between here and here, okay, and so these points in X become the inverse image of this region of Y, okay. So let me call this S, and so the inverse image of this entire interval in Y becomes the union of S, which is this, and the null set phi, which is an open set in X, which is just S, right, which is just this interval.
Okay, sir.
Okay. Yeah, so just to be clear, it's not the inverse function. You're talking about sort of the inverse image, which is different from the inverse function. Okay, it's the collection of points in X which gives rise under the mapping F into that region in Y.
Okay.
Okay. Okay. Okay, so let's do some more definitions about topological spaces, and we'll try to wrap up this idea of topological spaces today. Okay, so the first thing is, let's define what we mean by closed set. So we've defined the topology T defines an open set, defines the collection of open sets. So let's suppose XT is a topological space, and let's suppose A is some subset of X. Okay, then we say that this subset A of X is closed. Okay, it's a closed set if the complement of A, okay, which is X, all elements of X, after you remove the elements of A, if that set belongs to the topology T, okay, it belongs to the set T, okay, where T is this collection of open sets. Okay, so under this definition, you can see that X and phi, the null set, are both open and closed. Okay, so for example, if I take X to be A, so A is equal to X, then what is A complement?
Phi.
Phi, it's a null set, right? Because you X minus X, that is, you take out all the elements of X from itself, the thing we're left with is a null set. And the null set is closed because this null set belongs to T, because by definition T must contain the null set. And therefore you can say that under this definition, you would say that X is closed, okay, under the definition that we have. Okay, but also by the fact that X belongs to T, X is an open set. Okay, so remember, this definition of open set and closed set is not in the sense of open intervals and closed intervals. This is what we mean by an open set and a closed set in terms of topological spaces. Okay, so keep that distinction clear. Okay, so we'll see how this connects to open sets and closed sets. Okay, and similarly, you can also show that if A is phi, okay, A complement is X, and X belongs to T. Okay, by definition again, therefore phi is closed, but by definition phi also belongs to T, and therefore phi is open. Okay, so X and phi as subsets of, if I think of them as subsets of X, they are both open sets as well as closed sets under this definition of what we mean by open and closed. Okay. Okay, so maybe I can give you another example. So let's take the rail line with the usual topology. Okay, can you give me an example of something that is a closed set? Take a guess.
A single point.
A single point. Okay, so let's say a single point P. So what is the complement of the single point P? So if I call this A, what is the complement of the single point?
Union of two open intervals.
Yeah, or I mean, I can think of it as R. I remove this point, or equivalently, I remove this point and I have this open interval from -infinity till this point, and the open interval from P till infinity. Okay, so P is excluded. Now, is this a member of the topology of R, in the usual topology?
Yeah.
Yeah, because every open set and its unions, okay, so this is a union of two open sets, belongs to T. So A complement belongs to T. Does A belong to T?
No.
No, why?
Because it's a closed set.
It's a closed interval.
Yeah.
It's a closed interval, so it's not an open set. Okay, so A complement belongs to T, but A does not belong to T. Since A complement belongs to T, by definition, A is said to be a closed set. Okay, that is, this point is said to be a closed set. Similarly, you can show this for any closed interval. Okay, the complement of this closed interval, let's say 0, 1, is minus infinity 0 union, okay, open interval 1 infinity, and this again belongs to the topology T, and therefore you can see that a closed set belongs to a closed set. Closed intervals are closed sets. Okay, but also unions of closed intervals are also closed sets. Okay, so for example, if I take 0, 1 union 3, 4, okay, you can see what the complement of this would be. Okay, the complement of this would be minus infinity to 0, okay, and then union 1 comma 3 union 4 comma infinity, which belongs to T because it's a union of open intervals. Okay, and therefore this belongs to the topology, and therefore A does not belong to the topology, so A is not open, but A is closed. Okay, so A is a closed set. Okay, so unions of closed intervals also are closed sets. Okay, just like unions of open intervals are open sets. What about a half closed, half open interval? Is this a closed set? So let's say 0, 1.
No, sir.
Why?
One is
Because its complement will contain a half closed set too.
Right. A complement will be minus infinity 0, which is open, but it's a union with left closed, right open 1 infinity, which does not belong to T. Okay. So this kind of half closed, half open is neither a closed set nor an open set. Okay. Okay. Now, now let's define another property. Now that we've defined what is a closed set, so we define the closure of A. Okay, so if A is a subset of X, we define the closure of A as the smallest closed set that contains A. Okay, and this is denoted as A bar. Okay, this is called the closure of A. Okay, so for example, if I take 0, 1 to be a set, okay, then the closure of A is the closed interval 0, 1. It's the smallest closed set that contains A. Okay, this is the fewest elements that I've added. Okay, which contains A. Now the interior of A is the largest open subset of A. Okay, so the interior of A is defined as the largest open subset of A. So the interior of A, what would that be in this case?
A itself.
It's denoted as A0. Yeah, so in this case, A0, which is the interior of A, would be 0, 1, which is the largest possible subset of A. Okay, A bar would be the closed interval 0, 1, which is the closure of A. Okay, so it's just like I closed it by including the boundary points. Okay, 0 and 1. And the interior is defined as everything except those boundary points. Okay, so the boundary B of A is defined, okay, as A minus its interior. Okay, so in other words, the boundary of this, in this example, the boundary of A would just be what? Sorry, the boundary of A is the closure of A minus the interior points. Wait, did I get that right? No, sorry. I made a mistake. Okay, so the boundary of A is not defined. The boundary of A is indeed defined the way I've written it. Okay, so let's take two examples. So A can be any subset of X. So let's take A to be equal to 0, 1. Okay, what is A0? That is, what is the interior of A? We've already done this example just above.
A itself.
A itself. And in this case, what is the boundary of A?
The null set.
Is a null set. Okay, so an open interval doesn't have a boundary. Okay, but what if I had taken A to be 0, 1, the closed interval? Then what is, first of all, what is the interior of A?
Open interval 0, 1.
Open interval 0, 1. And then therefore, what is the boundary of A?
Point 0 and point 1.
Yeah, just the point, individual element 0, the singleton 0 and the singleton 1. Okay, so these two elements. So you see that as you might expect from a reasonable definition, right, an open interval has no boundary. Okay, the boundary is, a closed interval has a boundary and its boundary would be these two. Okay, let's do a more complicated example. So supposing A is the union of 0, 1 and 3, 4. Okay, what is the boundary of A if you work it out? So the first thing is you have to work out. Okay, let's do this example. So the first thing to do is to work out the closure of A. First thing is to work out the interior of A. Okay, so you want the largest open subset of A. What is the largest open subset of A?
Union of 0, 1 open interval and 3, 4 open interval.
Good. And therefore, what is the boundary of A? Which is this?
4 points, 0, 1, 3, 4.
Yeah, so it has 4 points as the boundary. Okay, so it's like this, okay, including the boundary points. And therefore, the boundary is these 4 points, 0, 1, 3, 4. Okay, okay, so you see that this boundary is easy to understand. Okay, the important point is that if you have an open set, okay, it is always disjoint from its boundary. The boundary is a separate set. The open set is a separate set. Okay, the boundary is not part of the open set. But a closed set always contains its boundary. Okay, and remember that closed sets are on the real line with the usual topology. You're talking about unions of closed intervals. Okay. So let's a couple of examples. So let's yeah, I think we've done this already. Okay, so okay, so for example, if we take A to be something like minus infinity to some A open interval, union B comma infinity. Okay, this is an open set. Okay, if we take A complement is the closed interval A comma B. The closed interval is a closed set, as we've already discussed under the usual topology. Okay. Another example is something like this. Again, we're just repeating a few things that we've done. So if A is equal to open interval A comma B, A bar, which is the completion, sorry, the, what did we call it? The closure, okay, of A is the closed interval A comma B. Okay, and the boundary is just the contains these 2 points A and B. Okay. Now, one important thing is that the open interval AB, the closed interval AB, left close right open, or left close right open, or left open right close, all of them have the same boundary. Okay. Wait. They all have the same closure. Okay, their closure is AB. They all have the same interior. The interior is AB open interval. I don't think they have the same boundary. Okay, this does not have a boundary.
I do. Because I mean the boundary is not conditional to being included in the set or not, right?
Yeah, but we define the boundary to be the complement of A0 in A. So the complement of the interior in A. So we define the boundary to be included in A. I should check this definition whether. So if we define the boundary to be the closure of A minus A0.
The usual way would be to define it as the same thing, but not in A, but rather in the universal.
in the closure. Is that what you're saying?
Or the closure, does it either way?
Yeah, but I think you want to define it as the open interval is not having a boundary. It doesn't really have a boundary. Okay. In the sense,
in other contexts, I've seen it. Seen it written as the open sets do have a boundary, but it's not included in the set.
yeah. So let me. Okay. So I've been following this Nakahara's definition. So let's just take a quick look at their definition. Yeah, so in their definition, A minus A0, okay, so it doesn't include the boundary. Okay, but they do confusingly say that the sets A, B, this line here, one second, they all have the same boundary, which is confusing because it's inconsistent with the definition that they've given. But there, there are a lot of typos in Nakahara, so I would not be surprised if this is a mistake. Okay, it's inconsistent with their definition at least. Yeah. Okay. Okay. So anyway, we can take either definition. Okay, as long as we know what we mean. Okay. So let's take the boundary to be A minus A0. Okay. We'll stick with the baseline definition given in Nakahara, and if we follow this definition, okay, or maybe it's easier to assume that this was the mistake in Nakahara. So if you assume this is the mistake, okay, then the boundary of 0, 1, the boundary can be outside the set. Okay, so the boundary of AB is then just open interval AB is just these two elements. Okay, and so therefore the boundary of all of these is the same. Okay. Okay, and similarly in Rn, okay, you can define the, this is an open interval in Rn, okay, or a union. Sorry, okay. It's a cross product of open intervals in Rn. But by this, what you mean is if I have two sets, right? I take all the element. So I take the element which is from one element in this closed interval, one element in this closed interval, one element in this closed interval, and that defines an element of Rn. Okay, and this is a closed set. Okay, you can argue that this under the same principle that this is a closed set under the usual topology. I don't know if I discussed this, but if you have x t, okay, and you have another y t prime, okay, so x and y are sets, okay, and t and t prime give x and y their topologies. You can define a product topology. Okay, I'm not sure if I discussed this, and it's not mentioned in Nakahara, okay, but I'll just mention this. So if you take x and y to be sets, you can define the cross product set, okay, which is basically the set of pairs in xy, okay, ordered pairs xy, okay, where x belongs to x, y belongs to y. Okay, and you can show that this product space, okay, xy, you can define a topology from this. Okay, it's easy to understand what that topology is, right? It's sort of ordered pairs of, you can think of this as so T contains open sets in X, T prime contains open sets in Y, right? And you can see, that there would be an easy definition for the topology on this product space, okay, which is just follows from here, okay, which is that you have to define a topology on this space. Let's call it T double prime, and this T double prime would be sets. So it would be open sets which contain elements A, B, such that A belongs to some UI which belongs to T, and B belongs to some UI prime which belongs to T prime. Okay, and if you define your T double prime like this to be this such open sets and their unions, okay, then you would get a product topology. Okay, So just like we define the topology on R, you can define the topology on Rn. Okay, so Rn can take on this this usual topology. Okay, it can be extended to Rn. Okay. Okay, so now a couple of more examples. Okay, so I think we did these. So if you have an open interval I01 on R, where you have the usual topology, then I is open. If you have, but however, the same interval I01, if you have the base space is R square, okay, which is the two-dimensional, you can think of it as a two-dimensional plane, then you see that in this plane, okay, this is neither an open set nor a closed set, okay, because if I come at it this way, this is closed, okay, but if I come from this direction, this appears to be open. So this is neither open nor closed. Okay, so it depends. It's not just that I can look at the subset A. I have to look at what is the space in which this space is embedded to talk about whether it's a closed set or an open set. Okay, under this definition of topology. Okay. Another thing that we can define is this notion of compactness of a topological space. Okay, so suppose xt is some topological space, and you have a number of sets ai, okay, which are subsets of x. Yeah, sorry, there's a question, Utkarsh.
Yeah, I just wanted to check, like for R square, the open set will be just a product, right? Like you described.
Yeah, so if I want an open set in R square, right, it would be something like this. So I can imagine a square like this, right, going from some a with the square without the boundary, right?
Yeah. Okay.
Right, that would be an open set in R square. Okay, and unions of these would also be open sets in R square.
Yeah.
Okay, and similarly in R3, okay, cubes, okay, or cuboids, okay, would be so it doesn't have to be a square, right? It can be a rectangle also. So in R3, cuboids would be open cuboids, that is without the boundary. Okay, those would be the open sets of R3. Okay, and their unions. Okay, and you can easily guess the generalization. Okay, now we can define this notion of compactness. Okay, so if xt is a topological space, okay, and ai are subsets of x, okay, then a collection of such subsets is called a covering of x if the union of these subsets is equal to x. Okay, that means intuitively, if x is a subset and I start taking subsets, sorry, if x is a set and I start taking subsets of this, and these subsets are such that they cover the entire space, okay, and when I take the union of all these AIs, okay, the union of all these AIs covers x, okay, is equal to x. Okay, so then you say that the sets of AIs together, they form a covering of x. Now, if all the AIs are not just any sets, but they are open sets, okay, that is that they are members of T, okay, the topology T, then this covering is called an open covering. Okay, so can you give me an example of an open covering of the rail line with the usual topology?
A comma B open interval where A and B belongs to real line number.
Yeah, okay, so for example, I could just take these sets, sorry, open intervals, but I take all open intervals. Okay, all open intervals, I take these to be the AI. Okay, this is not everything in T because T also contains the unions of these, and then all of these AIs together, they cover the rail line. Okay, but I could take a smaller subset of these AIs. Can you give me a smaller subset of this that covers the rail line? So right now this is things like, let's say 1, 2, but it also includes things like 1.5, 3.5, right? Which is obviously a redundancy if I'm trying to just cover A with the minimum number, the rail line with the minimum number of possible sets, possible open sets.
Maybe the set X itself.
Yeah, the set, okay, so the set X itself, right, is an open set, right? So the set X itself is an open set, and the union of X with itself covers the entire set. So indeed, yes, X by itself is a covering of itself. Okay. Okay.
So, yeah, we can constrain A and B like such as that they are integers and not.
Yeah. Okay. You can't do integers because, so for example, if I do 1, 2, 2, 3, I'm excluding the point 2. Right. So this would not be a covering if I just take the union of all such things, 3, 4, and so on.
Sir,
Okay,
but the set 1, 3 would be there, right? So it still covers.
Okay, I see what your point. Good. So if you have this kind of thing, then yes, you would cover all. This would also be a covering. So if I take each of these intervals individually to be a member of AI, of these AIs, then yes, this would also be a covering. Good. Okay.
So but it won't be equal to X, right? Because you're nowhere including 2 in your interval.
No, like you said, if you take 1, 3.
Okay, yes, sir.
Right. So as long as you have some integer I1, some integer I2, and all such integers, right? And you take all these open intervals, and you take the sets AI to be defined like this for every possible pair of integers I1 and I2. Then the sets AI form a cover, and it's an open cover. Okay. Okay, now we'll come to an important definition. Okay, this is a definition of something called compactness. Okay, of a topological space. So consider X. Okay, with some topology T. Okay, then you take and consider all possible coverings of X. Okay, then we define the set X to be compact. Okay, if for every open covering. Okay, that is, you take every possible open covering. So we gave some different examples of open coverings of R here. And now you take every possible open covering. And so in this open covering, the sets that cover X are open sets. So they belong, these are UIs which belong to T. Okay. If there exists a finite subset, okay, of J of I, such that the union, such that if so from this open covering, okay, I take members uj, okay, j belonging to j, and if this is also a covering of X, okay, but now the cover has only a finite number of sets. Okay, so in every example that we looked at here, almost every example that we looked at, we had an infinite number of sets, right? Because we had an infinite number of I1, I2 that we could choose, okay? And there was an infinite number of them that we glued together to cover X, okay? So now what we want to do is select a subset of them, and what we want to do is from that subset there should only be a finite number which cover X, okay? So for every covering, okay, so every example that you guys gave me, if we can find a finite number of those subsets that cover X, okay, then we say that X is compact. Okay. So under this definition, can you tell me whether the real line with the usual topology is compact?
If we take only X as the subset, that is only one number.
Okay, so the thing is, when you say you're taking X as a subset, that is one choice of covering, but we want this to be true for every covering. Right, so you see the difference? So indeed, if you take X to be the covering, then there's a finite subset of the sets that you're looking at. There's only one set, so that's set X, which covers the real line. Okay, but what we want is that this must be true for every possible covering. So even let's say the other coverings that you guys said. So if I take n1, n2 as integers, and I take this open interval, and I take all such open intervals. Okay, so this defines a covering, and this is an open covering. Can I find a subset of these AIs that covers the rail line?
Sir, no finite of these AIs, I mean, this integer, for example, will work because if you take the union of a finite number of these, then you'll always end up with a bounded thing.
Exactly, that's right. So if you take a union of any finite number of these, you will never cover the full rail line. Okay, so what does that tell you? Sorry, I couldn't hear you, Anish.
The real line is not compact.
The rail line is not compact. Okay, so R is not compact. Okay, actually, interestingly, there's a more general statement, okay, to be made here. If X is a subset of Rn, okay, so rather than just R, okay, then the set X is compact if and only if X is closed and bounded. Okay, so you need both these conditions to hold. Okay, for a subset of Rn under the usual topology. Okay, you need X to be a compact set. Okay, and for it to be both closed and bounded. Okay, so what do I mean by when I say this? So Rn has a usual topology, and then I can take a subset X of Rn, and X inherits a topology from Rn. Okay, inherited topology. Okay, or induced topology. Okay, now this subset X, okay, so the rail line itself we've already agreed is not a closed set, okay, sorry, is not compact, okay, but this X, which is a subset of Rn, can be compact if and only if X is closed and bounded, okay. So let's see some examples. So for example, if you take a point, just a single point in Rn or in R, okay, so let's say the point 0, this point is compact, okay, because I mean, okay, you can, I mean, you have to see what the topology is. The topology for this includes phi and this point O, 0 by itself. Okay, and now if I look at a covering of O, there's only one covering of this point 0, which is the set 0. Okay, so there's only one covering of 0, okay, or of the single point. And any subset of these coverings, okay, is finite, obviously, and therefore this point is compact, okay, by itself. But now let's look at another interesting example. So if I take the open interval 0, 1, okay, the open interval 0, 1 is bounded. Okay, that is, it's bounded in the sense of real numbers being ordered. So it's bounded. Okay, it has a minimum. I mean, there's a minimum. I mean, there are values in R which are less than this, and there are values in R which are greater than this. Okay, but it's not possible to cover this with a finite number of open sets. Okay, so therefore this is not compact. Okay, the space 0, 1 is not compact. So let's see what we mean by that. So for example, if you try to cover this 0, 1 by open sets, okay, so these open sets have to be subsets of this interval 0, 1, okay, because that's the inherited topology of 0, 1. So now, for example, what I can try to do is I can try to put open sets, okay, many open sets, and I can try to keep getting closer and closer to, you know, the end point, okay, but all these open sets have to belong to the open interval 0, 1. So for example, I could try something like 0 and 1 minus 1 by n, where I go on taking sets where n gets larger and larger, and I'm extending this one edge of the set closer and closer to 1. Okay. But what you see is that it's not possible to cover the entire space, okay, with a finite number of such open sets. Okay, and so again, this space will be non-compact. Just like the real line, this space is also non-compact. Okay, but the closed interval 0, 1, for example, okay, is compact. Okay, and this again you can think of the inherited topology, and the inherited topology will include not just open intervals in 0, 1, but it will also include points which left close, right open type points. Okay, they will belong to the topology T. Okay, of such a closed interval. Okay, so you have to actually work out what happens in that case. Okay. Okay, and finally, through this example, so if you take Rn plus 1, okay, this is in n plus 1 dimensions, and you take a sphere embedded in that n plus 1 dimension. So this is an n sphere. Okay, this n sphere inherits a topology from Rn plus 1. Okay, and this n sphere, by this theorem, we've not proved this theorem, but we'll just assume it's true. Now, this space Sn inside the Rn plus 1 is compact, okay, because it is both closed and bounded, okay, in Rn plus 1. Okay, it's closed and bounded in Rn plus 1. And therefore, this space is compact, okay.
Sir, I have a doubt. So in our earlier definition of compactness, we had we mentioned that the coverings have to be open. So how does half-closed sets sort of?
Like this one, you mean?
Yeah.
Yeah. So what you have to do is, when we say open set, okay, this is something to do with the topology. Okay, this is not about open intervals. So what you have to do is, now what we had defined was, for the topology of the real line, we had defined T to contain open intervals and their unions. Okay, and the set of such open intervals and their unions is what we defined as open sets. Okay. Now what we want to do is, we want to take a subset of this R of the real line. So in this case, the subset that we're choosing is a closed interval. Okay, we can always choose this subset. Okay, and now what we want to do is, we want to define the induced topology on this subset. Okay, and as I told you, one of the earlier discussions, how do you calculate this induced topology? The induced topology consists of all open sets. Open sets are by definition things that belong to T. It's not necessarily open intervals. Okay, in the case of real line, it happens to be open intervals and their union. And then from these open sets, okay, we take their intersection with this space A. Okay, so we take the intersection of these open sets with this closed interval, and you can see that those intersections, those intersections can be left closed, right open. Okay, for example, if I take the set -1, 3, okay, which is an open set in T, and I take its union, okay, with 0, 1, that will give me left close 0, right close 1. Okay, so sorry, its intersection, not its union. Okay, so I take the intersections, and those intersections can be closed sets, they can be half closed sets, and so on, half closed intervals, sorry. But all of these are now defined to be in the new topology of this new set X. Okay, so since they belong to the new topology, they are called open sets. Open sets is a nomenclature associated with topology. It is not an open set in the sense of an open interval. Okay, that's why I wanted to be clear about this difference between open sets and open intervals. Open sets have to do with, do they belong to the T associated with that space? Okay, open intervals are a property of the real line.
Okay.
Okay, which is why, okay, walk through this example again. Okay, you can watch the recording for this part. Okay, but and go back and look at the definition of induced topology. Okay, induced topology is basically where you see that you need to take intersections of these open sets, okay, with the subset subspace X that you're looking at. Okay. So, I mean, we haven't really talked about the topology that you induce on closed intervals, okay, but the topology that you induce on closed intervals will also contain these closed and half closed intervals as open sets of that topology. Okay. Okay, the next thing we'll talk about is this idea of connectedness. Okay, so we say that a topological space X is connected if it cannot be written as some union of X1 and X2, where X1 and X2 are both open, okay, both open sets, and X1 intersection X2 is a null set. Okay. Otherwise, X is called disconnected. Okay, so if X doesn't satisfy this criteria, X is called disconnected. Okay, so yeah, so one way to visualize this kind of topological space is you imagine that you have, let's say, you know, one space is, let's say, a set of points on a circle, okay, which is an S1, and there is this space, okay, which is, let's say, the rail line, okay, and your topological set X is this whole set, okay. Now you can see that this set X, okay, can be written as, so you can talk about the topology on this S1, okay, which is an induced topology from being embedded in, let's say, R square, okay, and so S individually has a topology, okay, and this R also has a topology, and together you can club them and talk about the topology of S1 comma R, okay, and now you can talk about this entire space as some X, okay, and you can see that this can be split into a set X1 and a set X2, such that X1 union X2 is equal to X, and X1 intersection X2, that these are disconnected spaces. Okay, so X1 intersection X2 is phi. So this is the sense in which you think about a topological space as being disconnected. Okay, it's your intuitive notion of what it means to be disconnected. Okay. So since it can be written this way, then you'd say it's disconnected. But if you have a space like this, which is the real line, okay, there is no way to write the real line as a union of two open sets, okay, which are disconnected from each other. Because like we said, so supposing you go up to, let's say, the point 0 and then minus infinity to 0 and then 0 to infinity, okay, you're excluding the point 0. Okay, to include the point 0, I have to take an open set, okay, which overlaps. So let's say if I go up to, if I try to stop at 0, okay, so if I take minus infinity comma 0, I have to take the union with something like minus 1 comma infinity, and this has an overlap with this set. Okay, so X1 intersection X2 is not null, and therefore X cannot be written as the union of two disconnected sets, okay, which have no intersection. So the rail line is connected, okay, and you know, some kind of space like this, S1 comma R, is disconnected. Okay, then you can talk about this notion of arc-wise connected. Okay, so if you take any pair xy belonging to X, if there exists a continuous map, okay, from the closed interval 0 to 1. Now, why the closed interval 0 to 1? It's basically just a way to define a path in the topological space. Okay, so you start with a closed interval 0 to 1. Here is my topological space T. I map, so 0, 1, also the closed interval, I can think of it as having a topology, right? We've already discussed the topology of 0, 1. Now I map this topology into this space X. Okay, so it's a function from this topological space to the space X. Okay, such that I remember that you have to choose 2 points X, Y, okay, belonging to this topological space X, such that 0 maps to X, 1 maps to Y, and if this map is continuous, okay, if the map is continuous, then you've basically drawn a curve in the topological space from X to Y, okay, and then you say that this space X, okay, if I can always find a curve, okay, like this, which connects X and Y, then you would say that this this topological space is continuous. Sorry, is arc-wise connected. Okay, that is, any 2 points X and Y can be connected by an arc. Okay, by a path from 0 to 1. So, so this is a map F which is continuous in the sense of continuity as we defined in topology. Okay, there's a third notion of connectedness, okay, which is associated with what are called simply connected spaces. Okay, so so again we draw maps, okay, from 0, 1, which is a closed interval, to a space X. Okay, and now supposing and we draw the maps in such a way that f of 0 is equal to f of 1. That is, if I have a point P here with 0 maps to this point P, 1 should also map to this point P, which means that we're drawing a closed loop, okay, in Nx. Now, if any loop X, okay, can be continuously shrunk to a point, okay, if this loop can be continuously shrunk to a point, then you say that X is simply connected. Okay, so let me give you an example of a space that is not simply connected. Okay, so for example, if you take a donut, okay, or a vada, okay, so you take something like this, and you imagine drawing this loop, okay, which is a map from 0, 1 to this space, okay, and let's imagine that this has the usual topology, okay. So this is, I can think about embedding this in R3 and think about the inherited topology on this space. And now what you can do is you can draw a loop, okay, which wraps around one arm of this Medu Vada, okay, like this. Okay, so as it goes around like this, now you see that there is no way to shrink this loop while keeping all the points on this loop on the surface. Okay, this loop, okay, I can slide it around the Vada, okay, but you can't really shrink it to a point. Think of this as a rubber band, okay. However, if I had taken another loop, which was just this rubber band sitting on top of, you know, one side of the Medu Vada, you can always shrink that rubber band to a point. Okay. Okay, you can shrink it by continuously changing it. Okay, but this, okay, this kind of wrapping, okay, around one arm cannot be shrunk to a point. Okay, so we'd say that this kind of space, which is called a torus, okay, is not simply connected. Okay, so this loop cannot be continuously shrunk to a point. Okay, so let's do a few more examples. Okay, so the rail line R is arc-wise connected. So every time I talk about R, I'm going to just talk about the usual topology. Okay, so we'll just assume the usual topology. So R is arc-wise connected. Okay, that is, if I take 2 points on R, any arbitrary points, P1, P2, I can always find a map from 0, 1 to P1, P2, okay, that is continuous, right? That is, I can always find something that maps to these numbers, okay? So in other words, you can find a function from 0, 1, okay, where 0 maps to P1, 1 maps to P2, okay, and there's a continuous function, okay, between these. Okay, it doesn't have to be increasing. Okay, it doesn't have to stay in this interval, right? This can be also be a continuous function. Okay, from P1 to P2. So R is arc-wise connected. Sorry, R is arc-wise connected. However, R minus 0 is not. Can you tell me why? So if I remove the point 0 from the rail line, it's no longer arc-wise connected. Why not?
That's because one could lie on the negative side of the real line, and so you'll not have any continuous mapping.
Yeah, so I could take, let's say, -1, okay, and if I remove the point 0 and I take the point +1, so let me call this P1, let me call this P2. Now there's no continuous path or function that I can draw which takes me from -1 to 1, okay. So R minus 0 is not arc-wise connected. Similarly, you can show that Rn, okay, for n greater than or equal to 2 is arcwise connected. Okay, so r square, r cube, these are all arcwise connected. Okay, and Rn minus 0 is also arcwise connected as long as n greater than or equal to 2. So even though if I remove 0 from the real line, I break it. Okay, but if I remove 0 from R2, okay, and I take any 2 points in R2, I can still draw a path which doesn't go through 0. I can go around 0. Okay, and therefore R2 is minor. Even with if I remove the origin, it's still arcwise connected. Okay. Okay, but all of these statements rely on the fact that you have the usual topology. Okay, if you have R with a discrete topology, so what is a discrete topology? Can you remind me what is the discrete topology on R? What would be included in T?
Closed intervals.
Closed intervals, and specifically points by themselves also.
Yeah.
Okay, so if I take R with the discrete topology, so now T includes things like A, B and their unions, but also closed intervals, okay, or individual points. Okay, so all kinds of things like this and their unions. So now this is the discrete topology. Okay, if I change the topology, okay, so it's very important that you're not just talking about the set R, but you also specify the topology. Because if I specify this topology, okay, you can see that now your maps will be discontinuous. Okay, so for example, if I take a point P1, okay, and a point P2, okay, so now these are the open sets of the discrete topology. Okay, remember again, closed intervals are not necessarily closed sets. Okay, they can be open sets. If you define the topology to include them, then they can become open sets. Okay, open sets refers to the topology. Okay, not the interval. Now, if I take the points P1 and P2, okay, I want a mapping from 0, 1 to P1, P2, okay, such that, okay, 0 maps to this point and 1 maps to this point, okay, and the interval between 0, 1, let's say, maps to something in between, okay, other points on R, okay. Now, here's the interesting thing, okay, so these are P1 and P2 belong to R, okay. So now here's the interesting thing. What do we mean by a continuous map? What we mean by a continuous map is that the inverse image, okay, that is the inverse image of this map. So this inverse image of this map is an open set of 0, 1. Okay. Okay. Now, and can you tell me again, what are the open sets of 0, 1? When it inherits the topology from the real line, what are the open sets of 0, 1?
Open intervals.
Open intervals. No, not necessarily open intervals. As I mean, I just discussed this a little bit earlier, right? It's not just going to be open intervals because you have to take the intersection with this closed set 0, 1. So it's not just open intervals where AB belong to 0, 1 and their unions. This is part of it, but this is not the complete story. What else should I include?
So 0 closed and right open.
Yeah, so some other point A, which is less than 1, and also things like B, 1. Okay, and unions of this with any of those open sets. Okay, so this becomes the collection of open sets of 0, 1. And now what we want is that these maps from 0, 1 to the real line are continuous, which means if I take the inverse image of this, okay, sorry, what was the definition that we had for continuous maps? The inverse image must be an open set. I think that was the definition. Yeah, so if X and Y are two topological spaces, in this case our space is 0, 1 and the other space is R, a map from X to Y is said to be continuous if the inverse image of an open set in Y, okay, is an open set in X. So can you give me an example? Where did we go? Yeah, can you give me an example of a mapping from 0, 1 to points in the rail line with this new topology, okay, with the discrete topology, such that the map is not continuous by this definition? This map should be continuous for every P1 and P2. Okay, so can you think of a choice of P1 and P2 such that you will not get a continuous map?
I guess if the mapping includes both P1 and P2, so the inverse image would also be the closed set 0, 1. So that would not be an open, sorry, the closed interval 0, 1.
The closed
Would that be-
intervals, the closed interval 0, 1 is part of these open sets.
Okay.
Because again, when you inherit the topology from R, you will take the intersection with 0, 1. So any open set larger than 0, 1 intersection with closed interval 0, 1 will be closed interval 0, 1. So I should include that in the topology table.
Are you inheriting this from the discrete topology or from the?
From the usual topology. It's inherited from the usual topology of
Okay.
R.
And your P1 and P2 are from the discrete topology.
P1 here so this topology on 0, 1 is inherited from the usual topology. Here this P1 and P2 in R are from the discrete topology.
Okay. All right.
So, but what we want to argue is that it's possible to find a P1, P2 such that it's not possible to get a continuous map from 0, 1 to P1, P2. By continuous, we mean that the inverse image, okay, would not lie in these open sets.
Can you consider that minus infinity to infinity?
Consider minus infinity. You have to specify a point, a specific point.
Minus infinity.
You have to give me a real number. Okay, let me give you a hint. Okay. See, what is different about the discrete topology? One of the things is that you include individual points by themselves, okay, in that topology. So, supposing I take just this point by itself, okay, as P is equal to P1 is equal to P2. And what I do is now the map from 0, 1 to P, okay, I just choose it so that every point in 0, 1
Sir, can we consider the map GIF of this interval 0, 1? I mean, then it would contain only 2 points, either 0 and 1, and one would be mapped to only 1, and the rest of the points would be mapped to 0.
So I said it again. So let's take P1 to, what are you taking P1 to be?
I'm taking P1 to be 0.
Yeah.
And P2 to be 1. And
okay.
And only these 2 points are included if I consider the map, let's say, floor function of floor function, if I consider the map.
So the map is continuous. So I map 0, 1. Okay, so yeah, so let's say I map everything except 1 to P1, and I map the point 1 to P2.
Yes, sir.
So So it is possible to find a continuous map from P1 to, but it is
one isn't a open set in your 0, 1, right? One is a discrete point, so it isn't an open set.
But P1, P2 are from discrete topology, so
no,
I think
1 is not from a 0, 1 is not from a discrete topology, right? So 1 would not be in an open set by itself.
Yeah, you want the map to, so okay, what do we mean by continuous map? You can map, of course, these elements to anything. Okay, but the inverse map should contain the inverse map. So the inverse image of that map is 0, 1, union 1, right? And this, but this does not, this whole thing is an open set in T.
No, if you just take an inverse map of P2, which is an open set in your P1 to P2 discrete topology, you'll get the
inverse map of P2.
Yeah, you'll get 1, which is not an open set in your usual topology. The inherited usual topology.
Ah, okay, thank you. Yes, good. Okay, yeah. So the yeah, okay. So sorry. Okay, so let's just clarify. Okay, so what we mean by continuous map is, so there's a map from the base space X. Okay, to the space. Now we choose a subspace of this space. Okay, which involves two open sets, P1 and P2. Okay, and now the claim is that if we take any open set in okay, in this space, okay, let's call this Y. Okay, if we take any open set in this space, the inverse image of this open set, okay, should be an open set in X. Okay. Yeah. Okay. So sorry. So more generally, okay, we can take the space in Y to be even like let's say. So we can take P1 to be, let's say, the point 0. We can take P2 to be the point 1. Okay, and we can imagine that now we've drawn a curve. So this is 0, this is 1, this is in Y, and X is the interval 0, 1. Okay, and now what we do is we draw a curve. Okay, so let's just take X is equal to Y. Okay, so we've drawn a curve from X to Y. But the point is that the inverse image of any open set in Y, okay, should map to an open set in X. Okay, but now open sets in Y include, okay, just these singletons P1 by themselves. Okay, or just a singleton P0, P1 or P2 by themselves. So which means that this open set should have an inverse image, which is also an open set of this topology. Okay, so for example, the inverse image of just the point 1, okay, which would be here, okay, would include just the point 1 in X, okay, which is this set. But as was just pointed out right now, singletons are not part of the topology of 0, 1. Okay, there's the element 1 by itself is not part of this topology. Okay, or the element 0 by itself is not part of this topology. So sort of the discrete topology, if you impose the discrete topology on R, it's very different from imposing the usual topology on R, because now you sort of break apart the real line into individual points. Okay, and those individual points also become open sets of the real line, and that's why it's called the discrete topology. Okay, so each one kind of by itself becomes each point by itself becomes an open set. Okay, and then basically you can understand why the maps, okay, once you have a discrete topology in R, why the maps are are discontinuous. Okay, Utkarsh?
So the closed interval 0, 1 will have a discrete topology, right? Not the usual topology.
No, the closed interval 0, 1 will inherit from the usual topology. Okay, it'll inherit a topology. That topology will include open sets and their unions. It'll include left close, right open, and right close, left open. And it'll include only one interval which is both fully closed, which is the 0, 1 interval. Okay, these will be the open sets. These and their unions will be the open sets of 0, 1.
Okay. Okay, no point, like there won't be any point in
There won't be individual points, and there won't be any closed in particular. There are no, I mean, in general, there are no closed intervals other than just the full closed interval 0, 1, which belong to the topology of this closed interval 0, 1.
Yeah.
Prakhar?
Sir, if we are saying that we can have half closed, half open intervals in this topology, then can't we consider the interval, the interval which is closed at 0 and open at 1? That would also belong to this topology, right?
Yes.
And if I consider the intersection of this closed 0, 1 and this this half closed, half open set, then
And which half closed, half open set?
I mean the closed 0, 1 and the half and closed 0 and open 1.
So the intersection, but it's not the intersections, it's the unions that belong to open sets.
Sir, but
oh, sorry. Okay, the intersection of this with 0, 1 should contain 1 by itself. That's what you're saying, right? Because if I take a finite number of sets, that's one of the axioms.
Yes, a third.
Yeah, okay, sorry. So maybe we shouldn't take this endpoint. We can just take a point in the middle, right? So let's call it half. The inverse of this, right? The inverse of this will be the point half, and the point half by itself here, okay, will not be a member of this topology. So I agree that okay, the endpoints are problematic because you include closed intervals, which include that point. Okay, and in particular, you'll have those points by themselves, but this will not have a discrete topology. Okay, the 0, 1 will not have a discrete topology. The endpoints are problematic. Okay, thanks. This is true. So 1 and 0 will belong to this topology, but points like half or closed intervals like half, 3 half, they will not belong to the topology of 0, 1.
So can we say that the mapping, the mapping of the floor function is a continuous one?
It's not continuous. Oh, yeah, I suppose so. The floor function would be continuous with the discrete topology because no, it would not. Yeah, maybe you can think of it as continuous. So the floor function would look like this, right? It's basically 0 throughout, and at 1 it jumps to 1, and you've taken the point 0, 1 here. Yeah, I suppose you could think of it as continuous. Okay, but regardless of whether you can think, okay, so the endpoint was a bad example, but if you take some point in the middle, okay, let's say half or 3/4, okay, that point is an open set in Y, okay, which is R with this discrete topology, and the inverse image of that is a singleton point in the middle of T, okay, of where T is the topology of 0, 1, okay, the closed interval 0, 1, and that is not part of the topology of T, and therefore there are no continuous maps, okay, that you can draw, okay, between two arbitrary points P1 and P2, okay, and so R is disconnected. Okay, when you change the topology. Okay, sorry, let me just do some more examples and then we'll wind up. Okay, so yeah, so now R square minus 0 is arcwise connected. Okay, that is if R square, as I said, if you remove the origin, it's still arcwise connected. I can always connect 2 points like this, but it's not simply connected. Okay, can you tell me why it's not simply connected? So if I remove the origin, it's no longer simply connected. Can you tell me why? Simply connected means I draw a loop, and that loop cannot be continuously shrunk to a point. So this loop can be continuously shrunk to a point, but this loop cannot be continuously shrunk to a point because I would have to I have to pass through 0, and 0 is not part of my topological space anymore. Okay, so if I go on deforming it, I can do this, but I can never quite shrink it to 0 because it's always circling that hole in the space. Okay, so however, if I go to R3 and I remove the origin, okay, so I remove the origin. Now I can shrink this loop to 0. Okay, I just move it forward, so I translate it in the y direction, and then I shrink it to a point. Okay, so R3 minus 0 is arcwise connected, and it's simply connected. Okay, and R square minus the rail line is not arcwise connected. R square minus the rail line is disconnected, right? Because if I remove the rail line, then the upper half plane and the lower half plane split into 2. Okay, so it becomes a disconnected space. For all practical purposes, arcwise connected will be the same as will basically mean the same thing as connected. There's some pathological examples where that's not true, but almost every case that you can think of, okay, it will be the case that arcwise connected means connected. Okay. Simply connected is a more special concept. Okay, it has to do with whether loops can be shrunk to points or not. Okay, now Sn, the n-dimensional sphere, okay, is arcwise connected. Okay, it's a connected space. S1 is also, in particular, S1 is connected, but S1 is not simply connected. S1 is a circle. Okay, and on this circle I can draw a loop. Okay, that loop can be a trivial loop in the sense I can go here and I can come back. Okay. Or I can do a non-trivial loop, which is I go around once. Okay, or I can do even more non-trivial loops where I go around. The mapping is such. Okay, this is a mapping from 0. 0 is mapped to this point, and then 1 is mapped to the same point again. Okay, but I can go around in any integer number of times. I can wind around. Okay, so this is called winding. Okay, and what you can see is that once I wind around some number of times, okay, I can no longer shrink that to a point. Okay, shrink in a continuous way. Okay, so this S1 or the circle is not simply connected. Okay, and if n is greater than or equal to 2, okay, then the circle, this n-dimensional sphere. So for example, if I have a sphere now rather than a circle, and I put a rubber band on it. So imagine drawing a loop which is basically mapping to these points. Okay, or even if I stretch this loop around, let's say, the equator, okay, of the Earth, right? I can always shrink it by pulling it to take that rubber band and shrink it by just pulling it to the North Pole. Okay, so so S2, okay, and in particular any higher n-dimensional sphere, okay, is simply connected. That is, loops can be shrunk to a point. And n-dimensional torus, okay, which is basically a cross product of S1 cross S1 cross S1. So in the example that we did, S1 is a circle. Okay, if I take another circle, that is something like this. So the way to think about a cross product space is at each point I have a circle. So let me call this the first circle A, second circle is B. At every point on A, I draw a circle B, okay, and so on. Okay, and I imagine that they're all connected through A. So what that effectively is going to give me, okay, is again my donut. Like this. So a donut or a torus is basically an S1 cross an S1, and I can think of it as this is one circle, and it's connected through many circles which I glue together like this and go around. Okay, and that forms a donut. Okay, and this is, as we've already discussed, is in general, this is also true for an n-dimensional torus, is the torus is arcwise connected, but it's not simply connected. Okay. 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 So now I'll just come to this last concept, and I might go a bit over time today. Okay. So this last concept is probably the most important one that we need about topological spaces. Okay, which is that the purpose of topology is really you want to classify different spaces. Okay, like you want to classify, is a donut different from a sphere? Is a sphere different from R2? Right? We want to classify these different spaces, and topology gives you a way to classify these different spaces. Okay, and so the purpose of topology is somehow to classify these spaces. And what we want to do is, in some sense, we want to say that two topological spaces are equivalent if they can be continuously deformed from one to another. Okay, so if there is some way, so for a topologist, okay, you would think about a coffee cup as having the same topology as a donut. Okay, in the sense that the coffee cup has a handle which has a hole in it, and you can imagine going on distorting the coffee cup. Imagine the coffee cup was made of clay, okay, and you go on shrinking it, okay, or made of rubber, okay, so you go on, you can stretch it, okay, or pull it, or push it around, but in such a way that the map is continuous, right? That is, you don't glue together, parts at opposite ends of the whole, okay? And so locally you can stretch and distort, but you don't connect things, which are in some sense far away or in different neighborhoods, okay? And you sort of move them around, and what you find is that by, squeezing on this coffee cup on one side, right, you can basically make it so that it effectively becomes this donut, okay? So the handle is already like half the donut, okay? And then I can squeeze this coffee cup, and the hole in the coffee cup is sort of immaterial because, okay, this is all one solid piece, okay? So you can continuously keep deforming it, okay, till it's sort of flat like this, okay? And then this flat part now has a handle, okay? And now this flat part, you can just compress it, okay? And now it looks sort of like just a donut, except this is kind of like, yeah, sorry, you have to think of the handle as a solid handle, okay? The solid handle is like the arm of the donut. Okay, so what we want is some kind of formal definition which formalizes this notion of deforming one space into another, and how you classify spaces based on whether or not they can be deformed from one to another. So in this way of thinking about it, you would say that the coffee cup is, you give it a word, okay, and that word is called homeomorphic, okay? Morphic means shape, homeo means same shape, okay? So they, sort of by a shape distortion, they're the same, similar to each other, okay? So the formal definition is something like this, okay? So suppose you have two topological spaces x1 and x2, and you have a map from topological space x1 to a space x2. Then this map is a homeomorphism if two things. One is it is a continuous map. That's easy. We've seen that before. But the second important point is that the map should have an inverse, okay? Not just an inverse image, but really an inverse, which means if I map from some point in x1 to some point in x2, okay, this map is 1-to-1, okay? And it's onto, which means that I covered the whole space in x2, okay? So everything in x1 has an image in x2, that's the definition of a map, but the map also covers the whole space of x2 and it has an inverse, okay? Which means every point in x2, I can uniquely find a point in x1 for which this map exists. So if there is, the condition is very simple. You just have to have a map from x1 to x2, okay? The map has to be continuous, and the inverse should exist, okay? And the inverse should also be continuous, okay? So so if these conditions are satisfied, okay, then you say that there is a homeomorphism between x1 and x2. These two topological spaces are in some sense identical, okay? So x1 is said to be homeomorphic to x2. So this relationship, okay, homeomorphism, is what we call an equivalence relationship. That is, if you say that x1 and x2 are related by homeomorphism, so that's typically denoted by this kind of symbol x1 related to x2, then you also say that, then first of all, it has three properties, okay? That is, x1 is related to itself. This is called an identity relation, okay? So it's obvious from the relationship that x1 is, any topological space is homeomorphic to itself, right? There's a simple map where I take any point x belonging to x and I map it to the same point x in x, okay? So that such a map exists. It's continuous, it has an inverse, okay? So you'd say that there is an equivalence relation, okay, between these two topological spaces. Second, there is an identity map. Sorry, this is the identity property of the relation. So these are properties of the relation. The second is the reflexivity property. If x1 is related to x2, that also implies x2 is related to x1. Okay, so this is obviously true because we're saying by definition that there is a map f, it's continuous, and f inverse, which is continuous, which means if I think about going from x2 to x1, I'll just use the inverse map. Okay, and therefore x2 is also related to x1. And the third condition is that there's a property of transitivity, which is if x1 is related to x2, if x1 and x2 are homeomorphic, x2 and x3 are homeomorphic, then x1 is also homeomorphic to x3. Okay, so such an equivalence, in general, when you have an equivalence relation which satisfies these three properties, there's an identity, reflexivity, and transitivity. What it does is it partitions your space on which these relations act. Okay, in this case, the space is topological spaces. It partitions them into classes. Okay, and all spaces within a class, okay, are homeomorphic to each other. So, but they're not homeomorphic to members of any other class. Okay, so for example, you could take one class to be, let's say, spheres of different sizes. So I can imagine stretching this sphere. Okay, that would be a continuous map. Okay, so intuitively, you kind of like just imagine stretching it. Okay, and that gives you a bigger sphere. Okay, these two spheres are homeomorphic to each other. And you can also say that this is homeomorphic to the open square. Okay, in R3, let's say in R3. Okay, so open balls, okay, like this, where you take the interior of a sphere and an open cube, okay, are homeomorphic to each other. Okay, as long as I don't include the boundary, okay, then this is basically covered by open sets, and these two can be and these two can be continuously deformed from one to another. Okay, in the sense of continuous maps in topology. Okay, so sometimes later when we talk about manifolds, instead of talking about the topology of Rn and defining the topology of Rn with open cubes, okay, or open cuboids, we will talk about the topology of Rn as using open spheres or open balls in Rn, as they're called. Okay, and so this idea, okay, of homeomorphism is very powerful because you don't have to restrict yourself to just talking specifically about spheres or specifically about cubes. Okay, you can just talk about all of these as members of a particular equivalence class, and all of these are homeomorphic to each other. They can be stretched and distorted into one. Okay. Similarly, a second class of objects would be, let's say, the coffee cup and the donut, okay, and other things which are homeomorphic to this. No matter what you do with the donut, you can't make a continuous map where I go on shrinking it and turn it into a sphere. This hole in the middle will always remain in any continuous mapping. Okay, so a sphere is not like a donut. Okay, so these belong to different equivalence classes. So this entire class of objects you can think of as one homeomorphic class of topological spaces. This is another class of topological spaces, which are in some sense equivalent to each other through these homeomorphisms. So intuitively, the idea of homeomorphisms is there are deformations which must be continuous. That is, you imagine that you can make these deformations without either tearing the space apart or without gluing points which are far from each other to each other. Okay, so as long as you can do these kind of deformations, those are continuous deformations. Okay, that's sort of the intuitive way to think about it. Okay, the rigorous definition is to think about continuity in the sense of how we've defined it for topological spaces. Okay, now let me give you a subtle example of spaces that are homeomorphic to each other. So if I imagine two circles, okay, one is something like this, and one is where you imagine that these circles are linked. Okay. You would think that there's no way to deform this, right, in a continuous way to get these linked circles. So you would say that these are not homeomorphic to each other. But surprisingly, if you go with the rigorous definition of what is homeomorphic, you'd find that yes, these are homeomorphic to each other. Okay. Intuitively, the way to see this is that the homeomorphism between these two, or the fact that they don't look homeomorphic, is actually a subtlety because these spaces, these circles, are individually topological spaces, right? That we're sort of imagining, right? But we're sort of imagining them as embedded within three spatial dimensions. Okay, so the fact that these look different is not really because the spaces are different, but they look different because of their embedding. Okay, they're embedded in three spatial dimensions. However, if you imagine that you took them to four dimensions, okay, so one way to think about it is, let me take one of these rings, okay, so imagine these linked rings, And imagine that instead of moving them in space, I move one of them in time. Okay, that's the physicist's way of thinking about a fourth dimension. So you move it in time. So now this ring only exists in the future. This ring only exists in the past. And so I move this future ring to a faraway point, okay, in space, and then I bring it back into the past. Okay, and now they're no longer linked. Okay, so you can see that the fact that they're linked is only an effect that is due to the fact that these are embedded in 3 dimensions. Okay, in 4 dimensions they can be delinked from each other. Okay, okay, and finally, now basically what we'd like to do is have a way to classify topologically equivalent spaces. Okay, that is, we'd like to classify members which are in class 1, class 2, and so on. Okay, so one way we can accomplish this is to define something called topological invariance. Okay, something that is a number or a group or some algebraic quantity that we can compute, which all objects in class 1 give you the same answer for, and all objects in class 2 give you a different answer for. Okay, or I mean, they could give you the same answer for some of these topological invariants, but in general they'll disagree for some of them. Okay, so roughly the idea is each equivalence class, okay, so let's say class 1 or class 2, can be characterized by some quantity, such as a number, okay, or a group or a ring. Okay, there's so these groups or rings are mathematical quantities. Groups you're familiar with, but basically you associate a group with the class. Okay, so you associate a group with the class, or you associate a number, some element of integers with this class. Okay, so there are different ways in which mathematicians try to do this. Okay, and the interesting thing about this is that this group or this number is the same for all members of the class. Okay, all members of the class, you can compute this quantity, and if they're all homeomorphic to each other, they will give you the same topological invariant. Okay, so the problem is mathematicians have not yet solved this problem of how to find all possible topological invariants. Okay, if you had all topological invariants, you could basically specify completely the properties of each class. Okay, we don't yet have a procedure to do this, but we have a procedure. So for example, you can imagine that class 1 or any class can be classified by some number of topological invariants. Okay, these could be groups or they could be integers. Now we don't quite know how to compute. We don't know what the full list of topological invariants is. We only know partial list. Okay, so given 2 topological spaces x1 and x2, we know how to compute some invariants up to some k, let's say, but there might be many other unknown topological invariants, okay, which we don't know. Now we can say that x1 and x2 are not homeomorphic to each other if any 2 of these topological invariants are not the same. Okay, the corresponding topological invariants disagree with each other. Then we can be sure that x1 and x2 belong to different classes. But if all of these topological invariants are the same, we still can't be completely certain that x1 and x2 are homeomorphic to each other, because some of these unknown topological invariants, which we've not yet discovered, may be different. Okay, but typically, what you assume, okay, without proof sometimes, is that spaces for which the known topological invariants are the same, those spaces are homeomorphic to each other, at least until you can rigorously prove the existence of such a continuous function between x1 and x2. Okay, so so this is exactly what's written here. So if any of these topological invariants II for x1 is not equivalent to II prime, which is for x2, then you can say that for sure that these are not topologically, these are not homeomorphic to each other. However, even if all the topological invariants for the known topological invariants are the same, okay, they may differ because of some unknown topological invariant. Okay, so let me just end with some examples. So let's take the closed line, okay, from -1 to 1. The closed line is not homeomorphic to the open line, -1, 1. Okay. There is no continuous map that takes you from here to here. And you can easily understand this by thinking about the fact that, remember, the topology of -1, 1 includes, okay, those left close, right open intervals and so on. Okay, and there is no way you're going to get a one-to-one mapping between these 2 spaces. Okay, and one other way to see this is -1, 1 is a compact space. Sorry, -1, 1 is a compact space. The closed interval is a compact space. This open interval is not compact. Okay, so compactness can be one way to classify topology. Okay, this is not a group or ring, it's just a property of the topological space. Is it compact, not compact? Non-compact spaces and compact spaces are never homeomorphic to each other. Okay. The parabola y is equal to x square is not homeomorphic to a hyperbola. Why is that? Well, a parabola is like this. Okay, a hyperbola has two branches. Okay, so you cannot intuitively you cannot deform this in a continuous way to get a parabola. Okay, so a parabola is arcwise connected. Another way of saying it is the parabola is arcwise connected. The hyperbola is disconnected. It has two disconnected pieces. So connected spaces and disconnected spaces are not homeomorphic to each other. Okay, a circle is not homeomorphic to the real line. Okay, a circle is like this. A real line is like this. Okay. How can you see that they're not homeomorphic to each other? Well, S1 is compact. If I think about S1 being embedded inside R2. Okay. While R, if I embed it inside R2, is still not compact. Okay. The rail line embedded inside R2 is not compact. Okay. Okay. Now S1, the circle, is also not homeomorphic to a closed interval. Okay. -1, 1. Okay, even though both are compact and arcwise connected. Okay, so the circle is compact, it's arcwise connected. I can connect 2 points with an arc. Okay, this line is also compact, it's also arcwise connected. But the difference between them is that the circle is not simply connected, because as I told you, you can draw loops in around the circle. Okay, which wrap around the circle several times. Okay, and in fact, that's one way to classify one of these topological invariants is how many times the loop. The group of windings around this, and the group of windings is classified by integers, z. Okay, so that group of windings, we won't discuss it, but it's called a homotopy group. Okay, and versus this interval, okay, there is no way to draw. I mean, this space is simply connected. Okay, loops can be shrunk to a point in this space. Okay, another way to think about it is if I take the circle and I remove 1 point. Okay, so if I take the circle and I remove 1 point, then it becomes an open interval. Okay, and this is connected. Okay, but if I take -1, 1 and I break it by removing 1 point here, then it becomes disconnected. Okay, so this is another way to see that these two spaces are not equivalent or not homeomorphic, because if I remove 1 point, this space remains connected, but this space becomes disconnected. Okay. Another example is if I take x to be -π/2 to π/2, the open interval, y to be the real line. Okay. Then I can define a function from x to y, and here I can define it explicitly. I can define it to be tan x. Okay. And this is a one-to-one function. Okay, which is onto it covers the whole real line. And this is a homeomorphism. The inverse function exists on the interval -π/2 to π/2. Okay, so one thing that you can see is basically an open interval of any size, 0, 1, is homeomorphic to the entire real line. Okay, the way to think about that is if I have an open interval, I can imagine stretching it, go on stretching it forever, and it basically covers the entire real line. Okay, and so this is one intuitive sense in which you can think about the homeomorphism between any open interval, finite open interval, and the real line. So boundedness, okay, or something being large on real numbers, that is not a topological invariant. Okay, that is not a topological invariant quantity. So in some sense, topology doesn't really have anything to do with metric. It doesn't have any measure of distance or size. Okay, in it. Okay, that notion of distance or size will come much later when we talk about metric spaces and introduce the notion of distance on a topological space. Okay, so just a few more examples. So you can talk about the open disk. Okay, that is a disk in R2 without the boundary. Okay, this is isomorphic to okay, and now what so this is isomorphic to the entire rail plane. Okay, so if I take a disk with the interior and I go on stretching it, it covers the entire rail plane. Okay, so these are isomorphic to each other. Now, if I have a disk where I take all the points on the boundary and I identify all those points as the same point. Okay, so it's like a chapati which you roll up and map all of these points to the same point. Okay, so you connect all of those points, the entire boundary here. Then basically it becomes homeomorphic to a sphere. Okay, a two-dimensional sphere. Okay, the surface of a sphere. Okay, and you can also take, since the disk is basically homeomorphic to R2, which is the entire rail plane, you can take the entire rail plane and you can glue the entire spatial infinity together to a single point, and that also becomes a sphere. Okay, so this entire spatial infinity, if I identify all the points at infinity as the same point and I wrap it up, okay, that also becomes a sphere. Okay, so the general way of saying this is the sphere in n dimensions is like taking Rn, the n-dimensional space of real numbers, and I identify the point at infinity as a single point, okay, in that topology, and I take the union of Rn with that single point, that becomes an n-dimensional sphere. Okay, and finally, a circle is isomorphic to a square, okay, or the generalization of this is open balls are isomorphic to open sets, okay, or this cross product of open sets. So instead of talking about the topology of Rn using these open cuboids, we'll talk about this idea of open balls when we talk about manifolds. Okay. We'll talk about open balls as defining the topology T of Rn. Okay, open balls T will define the topology of Rn. And this a circle is also homeomorphic to an ellipse. Okay, it can be stretched into an ellipse, right? It doesn't have to be a regular shape over here. Okay, so it can be any loop like this. This is also homeomorphic to a circle. Okay, so that's it. So we'll stop here. Any questions? We can take them now.
Hello.
Yeah, okay.
So for the last two examples, you were kind of interchangingly using isomorphic and homomorphism. So is there any difference between the two?
No. What I really meant to say was homeomorphism, not isomorphism.
Okay.
Okay. Well, okay. Is the homeomorphism and isomorphism? I think it is. So what is the formal definition of an isomorphism? Yeah, so an isomorphism, okay, so an isomorphism is a one-to-one correspondence between two sets, in this case, two topological spaces, that preserves binary relationships between elements of the set. So if I take any two elements of the set, the relationship between those is preserved under this, and I think that is true for a homeomorphism. So homeomorphisms are a type of isomorphism between two topological spaces. Isomorphism is the more general term. Homeomorphism is a specific isomorphism. Okay, it's a way to say that two things are identical in some sense.
Okay.
Okay, any other questions?
Hello, sir.
Yeah.
Sir, can you explain that example once more, that linked circles going into the R4 space? How are they homeomorphic?
Yeah, linked circles in R4. So if you think about these two linked circles, imagine now that I leave one linked circle in the past, okay? And one linked circle I only think of in the future. So in other words, I'm thinking of a time axis also, besides my X. So I can't draw it because this to draw the linked circles, I need an X, Y, and a Z coordinate, okay? But roughly speaking, if I think of one linked circle at X, Y, and the other linked circle at the same X, Y, I, instead of moving it in the Z coordinate, so this is an X, Y, Z space, I move it forward in time, okay? So this circle and this circle, if I move it to the same instant in time, they're linked. If I move this to a future instant in time, this is not linked because it's at some other point in space-time. right? So this
Yes,
circle only exists at t is equal to 0. This circle only exists at t is equal to some t naught. And now I move this circle to some other place in space and then bring it back here, right? And then I can see that they're t-linked from each other. Right? I mean, this is just a mathematically imagining the operations of deformations, right? Of this continuous distortion. Okay, the continuous distortion you have to imagine is not occurring in R3 but occurring in R4, which is including a time, like a time dimension.
okay, sir.
Okay, any other questions? Okay, if not, let's stop here and we'll meet on Monday. Thank you. Bye-bye.
Thank you.